After discussing the statically indeterminate problem, let's move on to stresses on inclined planes. Similar to the axial load, in the pure torsion case, we also have stresses on the inclined planes. Now, a bar is under a torque like this. For the square element inside the bar, it will have the shear stress sketched in this way. Since we know that the shear stress tau xy equals to tau yx in the previous tutorial, then we can sketch the stress element in this way. Therefore, we can derive the direct stress and the shear stress acting on this inclined plane by using this triangular wedge. Next, we decomposite tau xy and the tau yx in the direction of x alpha and y alpha. Now we do the static equilibrium of this triangular wedge stress element. Consider the area of the inclined plane to be dA. Then the area of this surface will become dA cosine theta, while the area of the surface at the bottom is dA sine theta. Since the stress on both of the surfaces are the same, which are tau xy, then we just simply write it to be tau. By checking the static equilibrium, we decompose those two forces into the x alpha and the y alpha directions to get those two equations. Consequently, we will have this. By simplifying the equations shown above, we can have the direct and the shear stresses on the inclined planes. The direct stress in the alpha degree inclined surface is given by tau sine 2 alpha, while the shear stress of an alpha degree inclined plane is given by tau cosine 2 alpha. Now let's talk a little bit about the angle of inclination alpha and some special cases of stress elements of pure torsion. For every inclined element, there are two alpha surfaces, namely here and here, as well as two alpha minus 90 degree surfaces, namely those two. How do you obtain the value of alpha? Consider originally you have an element like this, it is not inclined. Next, you rotate it by an angle of alpha counterclockwise. Then the element will be like this. This element is rotated counterclockwise by an angle of alpha. So this is how we can obtain the alpha. Then consequently, those two surfaces can be treated as alpha minus 90 degrees. The first special case we would like to discuss is the 45 degree oriented element. For this element, there are two 45 degree surfaces as well as two minus 45 degree surfaces. For those two values of alpha, for the red curve, it is representing the direct stress on the element. On the 45 degree surface, there will be maximum direct stress occurred on those two surfaces with the magnitude of the shear stress on that surface. For the negative 45 degree surfaces, you have the minimum of the direct stress, which means that for those two surfaces, there will be a compressive axial load acting on those two surfaces with the magnitude of the shear stress on that surface, but it carries negative sign. Besides, we observe that for both of the two angles, consider the purple curve representing the shear stress. There is no shear stress on those two alpha values. That means for the entire stress element, there is no shear stress acting on it. Another special case is the non-oriented element. Observe this curve, you can see that there is no direct stress acting on each surface. Besides, for this element, we only have the pure shear. At alpha equals to 0, the shear stress is the positive tau. Then we can draw this arrow first, which is tau. Then consequently, still remember our Valentine's Day joke? That is, they should have another arrow which is kissing this arrow. Similarly, you can draw the rest of the two arrows like this. So on this element, there will be shear stresses like this. The case I am going to describe here is actually not a kind of special case, but personally I think it is more special than general case. which is the 22.5 degrees oriented element. For this element, as you can see, at the 25.5 degree surface, the direct stress and the shear stress curve intersects here. Similarly, for the minus 67.5 degree surface, those two curves intersect here. We can draw the conclusion that the magnitude of the direct and the shear stress shown here are all the same. This is why I say it is relatively more special than other general cases. The magnitude is actually tau divided by square root 2. And similarly, for the 22.5 degree clockwise oriented element, you can observe that the magnitude of the direct stress and the shear stress are the same. Now let's discuss the stress elements under the general case. So just now we discussed 4 special cases for the stress elements under the negative torque. Now let's discuss about the general case. Under any pure torsion case, what will be the direction of stresses on a stress element in a bar? For general case, when we find there is a stress element inclined like this, observe that when there is a negative torque, there is a shear stress which is pointing upward on the right hand side of the stress element. Then this shear stress will be transmitted through this bar until it touches this inclined surface, and eventually, since this surface is better aligned with this vertical shear stress, then we can conclude that there is a shear stress pointing upward along this inclined surface here. But still remember our Valentine state stroke. Once you know one of the shear stresses acting on a stress element, you can draw the rest of them easily. Then all the shear stresses on this stress element is done and finished. What we need to do is just to find the magnitude of shear stress on this element. Next, about the direct stress acting on a stress element, you can observe from our general cases below that when the torque is negative, the direct stress on the stress element is tensile in this direction, kind like in this direction. So no matter how a stress element is oriented, in case the torque acting on the bar is negative, then we can say the direct stress is tensile in this direction and compressive in this direction. As you can observe in the previous special cases, for all stress elements except the 0 degree case, for the rest of the cases, there was always a pair of tensile stress and a pair of compressive stress acting on a stress element. So in general, for a stress element, there are 8 forces acting on it, 4 shear stresses, a pair of tensile stress, and a pair of compressive stress. Those stresses combined together will give 8 stresses acting on the stress element. And similarly, for the positive torque, you observe that on the right hand side there is a negative torque. There is a negative shear stress transmitted through the length until it touches this face, which is much better aligned to this vertical shear stress. Therefore, for this dominating surface, we call it dominating surface. We can draw the shear stress in this direction, following the direction of this shear stress. So a dominating surface is the surface that is better aligned. For the positive torque, the case is rather similar. This surface is better aligned to this vertically downward shear stress. Therefore, we can also draw a downward shear stress on this surface. Actually, I named this surface to be the dominating surface. So the definition of dominating surface is that this surface will absorb most of the shear stress transmitted from right hand side. When this shear stress is transmitted to this inclined surface, since it is better aligned to the shear stress here, then consequently for this surface it will be pointing downward. Similarly, this surface is also a dominating surface because it is better aligned to the vertically upward shear stress on the left hand side. Therefore, on this surface there is also an upward shear stress, and consequently you can draw the rest of the shear stresses like this. So the two arrows are pointing to each other. However, for an element in the positive torque, it is tensile in this direction, while it is compressive in this direction. Here is some summary. For shear stresses, first determine the dominating surfaces as we mentioned. and then draw the shear stress on that dominating surface following the direction of the vertical shear stress. Then you can draw the rest of them easily. To draw the direct stress, for positive torque, it is tensile in this direction, while it is compressive in this direction. For example, for a stress element in positive torque, the positive torque means that there are two shear stresses like this on the left and the right hand side of the stress element. So for those two dominating surfaces, we can immediately draw the shear stress on it, and also we can draw the rest of the shear stresses. Besides, since it is in the positive torque, it is tensile in this direction. That means the direct stress is sketched like this. Since for each stress element, there is a pair of tensile stress as well as a pair of compressive stress, then we can conclude that there is also a pair of compressive stress acting on it. So this is just how you determine the direction of the stresses on this piece of material. In fact, in order to determine the magnitude acting on it, you have to use our two equations introduced before. So those things are just for you to determine the direction, while those two equations are used for you to determine the magnitude. Besides, on the textbook, there is also an important conclusion. The relationship between the maximum shear and the normal strain in the pivot torsion is given by the maximum axial strain equals to 1/2 of the shear strain.